In the early 2000s, I watched firsthand as my mother and some colleagues created a newspaper called Vest. Despite early success becoming the country's largest newspaper, they dismissed the rise of Web 2 and social media, leading them to feel the loss of ad revenue when Web 2 solidified, closing their doors and pushing my mother into early retirement. As we journey forward in this AI revolution, I'm reminded of the words of Mark Twain. History never repeats itself, but it does often rhyme. So let's actively engage and shape our future. Hi, Amelia, dad of these two wonderful girls on screen, and a principal engineer at Klarna in my spare time. I was one of the first three engineers at Klarna to volunteer and work with LLMs. Since then, I've successfully led 2 product implementations, and I'm a general advisor to many others throughout the organization. Oof, OK. So Bernard Shaw has a famous saying, all professions are a conspiracy against the laity. This means that professionals invent jargon in order to optimize communication between them, making it difficult for an uninitiated person to jump in on the conversation. This is likely why you find this image intimidating if you're not initiated in AI. Let's try to fix it a little bit. That's a little bit better. But as we journey together for the next 25 minutes, I'll try to give you an intuition around all of these topics. And don't expect to become AI experts after this talk, but rather expect that you will have the tools to make decisions on when and how to apply AI in your daily work. And don't worry about AI taking our jobs. It still has the memory of a goldfish and is prone to occasional hallucinations. All right, so most of us here develop software products for a living. And over the years, we've learned that software products are composed of many different files that contain complex logic that provide functionalities to our users. Neural networks break this traditional mold. They don't really contain any source code outside of the training data that they were trained on and the logic that was used to train them. The output of that is one file. The key difference here means that there are no engineers designing the inner structure of the neural network. So the behavior of the neural network is not controlled by its builders. Artificial neural networks are based on biological neural networks. On screen, we see a biological neuron. On the left, we see the inputs of the neuron, also called dendrites. In the center, we see the neuron's body, and it has an activation function allowing the neuron to activate when a certain threshold value is reached from the inputs in its dendrites. When the neuron activates, it sends a signal on its output, also called the axon. The output of one neuron is connected to the dendrites of another via a synapse. The synapse has a connection weight, signifying the strength of the connection between these two neurons. So a good way to imagine how these networks work is to just imagine listening to music. So let's imagine that you're listening to music, and air vibrations travel to your ear canal, stimulating your eardrum and your cochlea nerve. The cochlea nerves sends electrical signals to something called perception neurons. Perception neurons are just the first neurons in your neural network. And they're very simple, so they would activate when they hear simple notes, like maybe they hear bass and they activate. In the next layer, these notes will start to be put together. So you may start to get a sense of musical motif. So in the next layer, these musical motifs will combine together, and you will start understanding choruses and verses. Finally, in the top layer, you recognize the song, and you go, OK, well, that's a song I like, and you turn up the volume. So your biological neural network has learned to make your neurons work together to this pattern of signals into a song that you like. OK, this looks complicated, but don't try to parse everything right now. I promise you that in the end, this is middle school maths, and I'll try to show you in the next slides. But what's important to understand here is that on the left, there's inputs, similar to how a biological neuron has dendrites. Then we have a weight, which is the connection strength of each input to the synapse connection in a biological neuron. We have an activation function that mimics the body biological neuron. And then we have a bias, which is the threshold value where the neuron will activate. And of course, we have an output that's the axon of a biological neuron. All right, so let's imagine one neuron, one input neural network. And in the beginning, all artificial neural networks have their weights, that's their connection strength, and their biases, their activation threshold, selected at completely random. So let's select 1 and 5, 1 for the weight, and 5 for the bias. We can also select an activation function 1 times x to make things very simple here. So let's say that we feed an input of 3 to this neural network. So if we calculate, we'll get an output of 8. However, let's say that based on our training data, we want an output of 95. So we can mask out the weight, and well, you don't need to really solve this. If you were to solve it, you would get that to get an output of 95, we need a weight of 30. We would plug in this new weight into the neuron and get a new neuron. Now we plug in the input of 3 again, and we see that we get the desired output of 95. So this is essentially how neural networks train and learn. If we scale this concept to the levels of GPT-4, who according to leaks has 1.8 trillion parameters, that's different weights and biases, you can see how GPT-4 can reproduce any output number based on any input. But how do these neural networks represent words if they only work with numbers? Well, in short, they map the words into numbers. But in reality, during the training process, the neural network learns the most common character pairs and marks those as numbers. This allows it to have a much more optimal vocabulary that can serve many different languages, rather than having the combined vocabulary of all languages around the world. The numbers that we get through this process are called tokens, and they become the input of the neural network. The process of converting the words into numbers is called byte-pair encoding. OK, but the neural network can't really function with these numbers, and that's because they're sequential in nature. So let's imagine that we want to encode a cat and a dog. So let's say that we encode the dog as number 3 and the cat as number 4. If we feed this directly to the neural network, it will learn that the cat is somehow greater than the dog. So to prevent this, what we do is we convert these numbers into something called sparse vectors. Sparse vectors are very highly dimensional vectors. They are in the dimensionality of the vocabulary of the neural network. And they have zeros everywhere except on the position of the token position. So let's say that we have a neural network that has 5 tokens, that's 0 to 4. The encoding into sparse vectors would look something like what's on screen. The process of creating these sparse vectors is called one-hot encoding. So now again we face a problem. The neural network can't really work with these sparse vectors because they contain mostly zeros, so they don't really contain any information. So we need to somehow compress the sparse vectors to get a condensed meaning that the neural network can learn from. This compressed representation of the sparse vectors is called an embedding. A best way to explain an embedding is to explain how an autoencoder neural network works. Now, an autoencoder is a very simple neural network. It has an encoder, a decoder, an input, an output, and a code in the middle. The input and the output are both greater in byte size than the code in the middle. So this forces the neural network, as it learns, to learn how to compress the input in order to get a similar output. So let's take an example. Let's say that we feed the Wright brothers invented the first successful airplane into an autoencoder that has been trained on much of human history. What we may find is that the autoencoder compresses down this sentence into its core meaning, and at the output, we may get Wright brothers built the first flying machine. Now, this output has different words, but the context is preserved, and the code in the middle is where the embedding is generated. Stable Diffusion, the most popular open source image model out there, was trained on 160 million images. That's 100 terabytes of data. The output model from that training is 2 gigabytes in size, and that output file is able to accurately reconstruct all of those 160 million images. This is a 50,000 to 1 compression, unheard of in any other industry. This experimentation with embeddings and compression led Marcus Hatter from Google to prove that the optimal behavior of a rational agent is equivalent to compressing its observations. In other words, intelligence is compression. This is very intuitive if you think about it, because all of us here don't remember our history books verbatim, but if we were to be asked of a specific fact in those history books, we'd be able to reconstruct it. When we create these embeddings, a fascinating pattern emerges. They cluster in multidimensional space based on their similarities. So if we take an example like the Wright brothers invented the first successful airplane, and we embed that, and we also embed the first flying machine was built by the Wright brothers, we may find that those two vectors are very close in multidimensional vector space. This is because they both capture the same meaning. And if we embed a lot of sentences about facts throughout history, we may find that sentences about the Wright brothers clustered together, sentences about Tesla may form another cluster, and then you may see some overlap between them, and you may see other sentences throughout the space cluster based on their meaning. If you really think about it, this is also intuitive, because during the training process, the neural network is fed massive amounts of data that it's forced to compress. As it's forced to compress this data, it must assign similar value in this data representation based on the similar meaning of the sentence. So we can use this clustering property of embeddings to find sentences that are similar in meaning. One way to use them is by applying something called a cosine similarity. A cosine similarity is just the cosine of the angle between two non-zero vectors. And if we get a value of 1, that indicates a high similarity due to the cosine function. Now, this example is two-dimensional, but in reality, these vectors are thousands of dimensions big. So in this multidimensional space, the cosine of the angle holds a lot of value. There are other ways to use embeddings and their mathematical properties. Like there's a very famous example of the embedding of king minus the embedding of man plus the embedding of woman equals queen. There's also other algorithms you could look at, like isolation forest and k nearest neighbor. Those are outside of the scope of this talk, but I encourage you to look them up right after. OK, so transformers are an advanced type of neural network. They use something called an attention mechanism. A good way to imagine how an attention mechanism works is to imagine the Grand Symphony Orchestra. So in the Grand Symphony Orchestra, we have a conductor and we have musicians. So let's say, imagine the violinist playing his music and focusing on it. And then when the conductor signals, the violinist may look up and shift their focus and start focusing with the viola section. This is how attention heads direct the focus of a neural network to specific parts of the input, to only the parts that are relevant. So let's take an example. Like if we feed our sentence, the Wright brothers invented the first successful airplane into a transformer neural network. We may find that the first attention head will focus on the Wright brothers to signify their identity. And the second attention head will focus on invented and successful airplane to signify what their invention was. These outputs are put together, and the sum of them is fed into the rest of the neural network, allowing it to have a lot of context about which parts should it process first and with more importance than others. Okay, so now we've covered a lot of topics that make up LLMs and GPT. So at this point, we're ready to put everything together and start discussing how LLMs work. So the primary task of an LLM is to predict the next word in a sequence. So if we feed, for example, the Wright brothers invented the first successful into an LLM, we may get airplane as the output. Now, if we want to get another word, we take this output and we feed it into the next input, and we ask again, what's the next word? And the LLM may predict flight. So this property of predicting the next word in a sequence is what makes LLMs a sequence predictor. And the property of feeding the output from a previous prediction into the next one is what makes them an autoregressive model. But GPT doesn't understand words. So it needs to use byte pair encoding to convert any words in its input into tokens. And of course, we learned that we can't really work directly with the tokens, so we need to do one-hot encoding to convert the tokens into sparse vectors. Now, the sparse vectors are, again, very inefficient, so GPT learns an embedding function to embed them and compress them. But when this embedding function is made, the sequence of the original input is lost. And this is very important for LLMs because they are sequence predictors. So to preserve the sequence, GPT uses something called positional encoding, which applies a synostial function to the input to add sort of like markers in the embedding of where the original input was. It's kind of like adding markers along the trail. Then next, GPT will feed the output of the embedding step into a transformer and use the attention mechanism to focus on what's important in this input and what it should process. So unlike our example where we had 2 attention heads, GPT uses 96 attention heads in GPT-3. Next, after the attention step, GPT will feed the output into a feed-forward neural network. And this feed-forward neural network is many, many layers deep. This creates a new problem where the original input is eventually lost throughout the neural network. So to prevent this, GPT re-adds the original input to the output of every layer in this very deep neural network, kind of like an echo throughout the network of the original input. This helps it stop something called the vanishing gradient problem and helps it train. Next, GPT feeds its output embedding into a decoder, similar to our autoencoder example, and we get the next word prediction. OK, so with everything that was shared above and your previous knowledge of ChatGPT, it's easy to anthropomorphize ChatGPT and give it properties equivalent to a human. We do this a lot in terminology. We have a term called hallucinations. What a hallucination is a wrong next word prediction. While LLMs do possess intelligence and a worldview, this intelligence and worldview is very statistical in nature. So it's not derived from conscious thought. A good way to explain hallucinations is to start by explaining what a query optimizer is. So a query optimizer is a component we use daily with database development. This is a statistical component that has a statistical understanding of the inputs of a table, not really the entire content. So let's say if we have a table that contains the age of different people, we may have a query optimizer that has the minimum value in that table, the maximum value, and the median and the average. So if we were to ask this database for a person that's 2,000 years old, the query optimizer will directly see that this is a value that's out of bounds and respond that that's not found before even querying the table. OK, so let's imagine a very simple table of ID, company name, location, and then these are the values. So if we ask the database with this table, where's the location of Apple? It will say California, of course. But if we were to ask where's the location of Klarna, it would respond with 404 not found because Klarna is clearly not in this table. However, if we were to ask the query optimizer for this table, where is the location of Klarna, it will, of course, respond. There's a 50% likelihood that Klarna is in California. There's a 25% likelihood it's in Amsterdam, and a 25% likelihood it's in Stockholm. And we're not in California today. So this is exactly the essence of how GPT hallucinates. It doesn't really derive new meaning or conscious thought on what to say next. Rather, it's just filling the gap of its training data with statistical understanding about what should go in there. And of course, we wouldn't really ask a query optimizer for a directly knowledge-based question. We would just use it to find the most optimal path in a table to find data. This leaking of statistical information into the output of language models is not something that we have solved today. Solving this problem will require a completely different approach to how we design LLMs. But in the meantime, we do have ways to mitigate this. One way to mitigate it is called retrieval augmentation. What retrieval augmentation is before we ask the question to an LLM, we first use this question to find data that supports answering it in our knowledge base. So our knowledge base can be a database or a knowledge graph or any other storage medium. As long as we are able to extract relevant information that supports answering the question, and we feed this together with the question to the LLM, we get better results on the answer and less leaking of this statistical information. Stanford did a study where they analyzed the most popular retrieval augmentation systems out there, among which Bing, and they found a 52% correlation to any one answer to the retrieved information. This means that the problem is not solved, but a more than half correlation to the retrieved information in any one answer means that this is viable for production use. So now you're thinking, OK, well, Ilya, you told us this is all very revolutionary and that it can do a lot and change our industry. But how can it really do that and compare with human intelligence if it's just a stochastic parrot? Well, what is intelligence? We saw that Marcus Hatter believes that intelligence equates compression. But what is its definition? This is a very disputed topic, but if you look up online, one definition that you'll find is the ability to acquire, apprehend, and apply knowledge in a behavioral context. So we've been able to acquire knowledge for a while now in our knowledge bases, whether it is our knowledge graphs or databases or what have you. And we always needed to put that knowledge in a structured format, structured data. We also needed to write an empirical logical code base to use that knowledge, whether it's from our knowledge bases or other inputs. So this is what's being disrupted today. We no longer need a fully empirical logical code base to use our knowledge. We can now instruct a large language model to use its statistical understanding about the world to apply our knowledge. Now, it will not understand our knowledge the same way that we do. It will understand it through statistics, which means that there's large parts of our knowledge that the large language model will not understand at all. But these parts we can supplement with empirical logic, leading to a replacement of much of which requires human intelligence today. OK, so with everything you've heard so far, hopefully you can start to see how applying large language models can be revolutionary to our industry. But building a large language model is a challenging feat. Luckily, with the efforts of OpenAI, Anthropic, Meta, Google, and others, we have a plethora of open source and proprietary language models that we can utilize. The open source models do require some setup to do inference, and that's actually random. But the proprietary ones are hidden away behind an API call, making AI very accessible to each and every one of us today. In a similar fashion how back in the 2000s, Web 2 and social media was very accessible to news reporters, and they didn't need to understand how the cloud works or how social media works. That's where we are today with software development and AI. So with what you have learned today and the ability to scale intelligence with foundational models, what will you apply AI to today? Will you build an automatic scraper that generates codes and can scrape emails? Or will you analyze the feedback from your users that's entered in free text that was deemed impossible before? Or will you just improve the search experience in your database by using semantic similarity? Outside of what you're already doing, what are things that you always wanted to do but were completely impossible? Like, for example, building the ship computer from Star Trek is entirely possible today. The limit is your imagination. I've seen observers of new technologies fade into obscurity with my mother's journey. Her passion grew and evolved into something that she no longer recognizes, leading her to abandon the industry. If you're like me and you like building tools for others, don't let this wave pass you by. It's clear that our industry will change, and it is clear that we will build tools in a different way very soon. You now have the chance to enter this revolution at its start and ride the wave as it grows. So don't be a spectator to this revolution, and thank you.